everyone, we're going to graph these functions, piecewise defined functions. These are the same, so I put them on the same video. The only difference is this last part right here. This is x is greater than or equal to 2, and this one is just x is greater than 2. And the first thing we're going to do is test for continuity at x equals 2 for both of these. So then we're going to graph it. So here's our first one we had. And here are the conditions, 3 conditions that have to be met to be continuous function. So basically it says condition 1. If condition 1's not met, we don't need to go to the other 2. So we have to see if f of c exists. So that just means, do we have, our c is 2. Because they want to see if it's continuous at x equals 2. So that means our c is at 2. So you just plug in 2 where x equals 2, and that is this one. So x can be greater than or equal to 2. So we're going to plug in f of 2 equals 2 times 2 minus 1. And that equals 2 times 2. So this is going to be, wait. So this is going to be 2 times, 2 minus 1. And that equals 3. So we do have a value. So condition 1 is met. Now, the limit means that we're going to take the limit as x approaches our c, which is 2, from the left and from the right. That means this would be from the left, because this is on the left side of 2. Any numbers less than 2 are on the left if you look at the graph. And any numbers bigger than 2 are to the right. So we're going to take the limit of x approaches c from the left. So that means we plug in that, and we get 2 plus 1, and that equals 3. And this limit should equal the limit as x approaches c from the right. So we already did that, and that equals 3. So we do have 3 equals 3. Okay, so condition 2 is met. Condition 3 just means all the numbers have to match. So our limit of c, which is 3, has to equal f of c, which was 3. So since these two numbers match, this is continuous. Now we're going to do the one where we don't have an equal sign. So we just don't have an equal. Now if you have that one, I'm going to erase this real quick. So if you have that one, our first condition is to check for f of c. Does f of 2 exist? And there's no place to put f of 2. We can't put it in the first one. We can't put it in the second one because there's no equals there. So condition 1 fails. Condition 1 fails. And we don't even need to go on to condition 2 and 3. So for our second one, it's not continuous at x equals 2. Now, let's graph these. So I'm going to graph the first one. For x is less than 2, I go to 2 on my x. Alright, and plug in 2, even though it can't equal 2. So 2 plus 1 is 3, but you do an open interval. And then you just go to the left. So I already know that the y-intercept is 1. And I know it's linear, so I don't really need to do a table there. So I'm just going to graph all these points here. Now, for the ones, all the numbers to the right of 2, we have 2x minus 1. So at 2, you plug in 2, it can equal 2, so that's going to equal 3. So if we do a little table here, this is our x, and this is our 2x minus 1. If you plug in 2 to this equation here, you're going to get 3. So you have here, but it can equal it. So closed circle overrides open interval. Closed overrides open. And then from there, I can just, let's plug in 3. 3 was going to go to 5. That's the slope is 2, so 3 goes to 5. And you know it's a straight line, so that's basically all you have to do. And there's where it shows that it's continuous. Now, if we did the other one is the same thing, but let's see, there's no equals. So it's that one. And what happens here is right in here at 2, there's no value. So that would be the graph of the second one. And that's why it's discontinuous at 2, because there's a point. This is called a point of discontinuity. Okay. So that's going to be important in calculus when you are taking derivatives and whatnot. All right, that's it. Thank you. Have a nice day. Bye-bye.